All right, boys. What we got here is we have a little selection of breaker bars. These are all half-inch drive, 12.7 millimeter drive. This particular one, this is a snap-on. I've had this one maybe, I don't know, close to 30 years, I think. I bought this long time ago, actually, and it's still in great shape, as you would expect for the kind of prices that you pay for snap-on gear. Now these are flea market finds here. These are Plum, the predecessor to Proto, and they're different lengths. And you see they got a different number. This is a 5467 and a 5468, and I imagine they had several that were a little bit longer. And this has the really cool little pebble finish, I call it, in there, and you can see that these are kind of configured the same. Now, I hate to admit it, but the other day, I had the idea for this particular video, and I said, you know what? I'm going to go into the evil empire and have a look around and find something that we can actually do a kind of a cool or not cool tool comparison. So I went into Harbor Freight and I bought this guy right here. Okay, and this is a Pittsburgh flavor 25-inch half-inch drive breaker bar. Okay, so this is I don't know, it's 570 millimeters. This one is 600 millimeters here. Okay, and so I thought what we would do is we'd do just kind of a basic comparison here. Now I think I'm going to take these out of the equation here since they're not generally available. I mean, it's kind of they don't make these anymore, unless you buy them on the antique market or whatever. So what I think we'll do is we'll compare the snap-on with the Pittsburgh. Okay, so let's go ahead and do that. We'll start, and then we're actually going to do some physical testing too, which might be enlightening. All right, well, let's start at the business end here, the head, and we'll take a look at the head here. Let's pull this cheese ball thing off of there. So get rid of that. All right, so let's just take a look at these to start with. So right away you see one of the major design differences here is the snap-on, and then also the Plum. They have the fork is on the handle side, and in the case of the Pittsburgh here, they've opted to put the fork on the separate piece. Now, why do you think that is? My guess is it's a manufacturing thing, is that this is more difficult to manufacture. This is simpler to manufacture, and then this piece looks machined, actually. To me, you can see the telltale marks. Or, maybe it's forged, I don't know. Actually, you know what, maybe I ought to look at the silly little plastic chingus. But let's just keep going here. So that's one thing. So right away, I see this and I see, well, this is kind of bulky, and this is a little more streamlined and a little neater. Okay, come on, I'm biased, all right? Just get with it and don't worry about it, all right? But we'll try to make this a fair comparison. So this thing it's got a nice feel to it. It's just the right stiffness. So if you point it somewhere and you got a socket on there or something, it's going to kind of stay. This, not so much. It's a little limp. Okay, maybe. This is also a fastener. I may be able to just kind of snug that down a little bit and then get a little more tension on that. So I haven't tried that, but it's a reasonable assumption at this point. So, all right. So the next thing that I'm looking at this pivot diameter here. And so that's the fastener head there, and you can see that there's a little bit of a difference there. So let's be conservative here and give it a little bit. So it's like a 5/16 fastener, or for our metric-minded folks, so it looks like an M8, okay? And then this one here, let's see, that's rotating, so I'm going to say that that's the full diameter there. This is 10 millimeter here, okay? So you got 2 millimeters more diameter on that than this. Yeah, I just don't like that looseness there. I have to get a metric gallon and try tightening that. Okay, so let's look at the detent there. I don't know, that's just a crimped ball. Let's check the spring force. Okay, that's pretty good. Spring force is similar. Now, let's see, that feels a little different. This one's got kind of a little click to it. That's okay. I think they might be using a different type of spring. Now this looks like it has kind of a pressed in retainer here, and it might even be bronze. It's hard to tell. It feels pretty hard. And this is just a hole that's been smushed over to retain the ball. So this is a little neater here. Let's check the diameter or the sizes here. Oops. Let's switch back to 495. Okay. This is a little. Oops. 497. Let's go this way here. 497. This way on this one. 493, 494. Okay, so they're reasonably square. This is just slightly smaller. The next thing that I notice here is this necking here. This looks a little thin. So we drop down to, I don't know, 415, and this is a full 615 here in that area. So although you're kind of, well, let's see, no, you are torquing in that direction, so that could be a significant difference there, because you're reefing on it directly against that. So okay, so let's zoom back out a little bit, and then we'll look at the overall, and then we'll go set up our torture test. All right, so right out of the gate, you'll notice that they've given us a little bit more length with the Pittsburgh model, and if you put them end to end like that, this is, I guess this is the 24-inch breaker is what they call this, and that's basically the overall length. Actually, it's 23 and a half, 595 millimeters, and then stem to stern on this one here is 640 millimeters. Or 25 and a quarter. They called it a 26, so these guys are generous, I guess, with themselves. So when we do the test, we'll make sure that when we put force on this, that we put it so that it's kind of in the same place. So it's kind of the readings on our strain gauge will be correlatable easily. So let's go. Let's go over to the steel bench and see what we can do with these things. All right. So we got a couple things over here. We got the tomometer here, which you guys have seen before. So let's get that set up. Now, just to refresh your memories, this is a ring dynamometer that I built, I don't know, quite a while ago now, and each division here, each thousandth of an inch is 100 pounds. And that was pure luck on my part that occurred. Okay. So now, what's the we got to think about this for a sec. So, you know, if you're reefing on this, oh, and I made this this block here that will allow us to clamp this, you know, in a fair manner. So, what do we, you know, let's just talk about it for a sec. What do we think is a reasonable amount of force that we could pull on that with? Okay. So I've been thinking about it a little bit, and I'm like, okay, well, body weight for sure. Okay, so I'm over 200 pounds, so I'm confident that I could pull on that over 200 pounds. And if I had two hands on it and my leg braced up against something, I could probably almost double that. Okay, so a reasonable expectation here is that we could put 400 pounds out here, okay? Something like that. So if I was designing this tool, and some of the guys that I've worked with that are big buff dudes, they could easily do 400 pounds. So now, this one here has a lifetime guarantee, so if I destroy it, which I hope I don't, because there's some sentimental attachment here, I can get it repaired or replaced easily. This, I believe, is the same situation. If this thing dies, I can probably just take it back and get another one. Let's try it. And you know, we're going to set 400 pounds at our as our kind of our working load there. Okay. So let me get this all set up. And oh, the other thing that we have to do here is we have to kind of compensate for the length difference. So what I'm going to do is I'll use a piece of this bull tape here, and I'll choke around this so that it's applying the force at the same leverage position on this one as it is on the snap-on one. So the readings will correlate, and we won't have to do any monkey business there to correlate those. So let me get set up, and we'll be right back. All right. So before we put the squack on these things, something else I forgot about is I wanted to demonstrate this and actually measure this value here. So this is my point of reference, this blue mark right here, which is equal to where I would be rigging this thing up here to make them equal. So let's see here. We're going from 5 to 8.5. That's 3.5 inches of float there in that one. Let's try this one here. This is the snap-on. Well, okay, so that's barely a contest there. So let's see here. That's about 6. So that's 2 inches versus 3.5. Now you can see that's physically snugger. And this is a used tool, by the way. This tool is 30 years old, or 25 at least. I bought this from Gordon Foxworthy, who was a snap-on dealer down in Pleasanton back in the day. He was driving a truck. Well, now I think he's a vice president, a big willy wig down there in snap-on land. So, all right, let's back up here, get back on track. So this is a little loosey-goosey here, but it's okay. You know, and don't get me wrong, buy what you can afford, right? It's better to have the tool than to not have the tool, and not everybody can afford snap-on or even want snap-on, right? So you use a breaker bar every 5 years, yeah, you don't need the Primoist tool. If you make your living with this, yeah, you can really appreciate the differences in those tools. All right, so let's get this combo meter hooked up here, and what we're going to do is just going to put a L choker around it here, and hopefully it's not going to slide too much on us there. Put it on my little blue mark there. Like that. You know what? I gotta double check something here. We're slack. Okay, we're zeroed. I did zero it. Kind of lined up with the world. And side here so I can see what's going on. All right, so let's go to 100 pounds. Oh, yeah, all right. Now we may have to do some conversions here, guys. My little this chrome plating is pretty slickery dickery dock there, so what do I want to do there? Can I do anything about that? Oh, you know what? I'll put a couple of hose clamps around there. Maybe that'll keep it in position. And like I said, it's a lot easier to do a nice comparison if we're working from the same spot. So let me get a couple of somethings on there. Okay, if that'll work. Sure, yep. Okay, I'm zeroed. I'm gonna tip this so maybe we can see the. I hope it doesn't go out of frame there. Let me check that shot. See if you can see that business there. Yeah. All right, that looks better. Okay, so pretty straight here. That looks straight. Got a little load on it. Oop, wrong way there. Let's go up to 100 pounds and see what we get here. All right, that's about 100 pounds there. Everything's looking pretty good there. Oh, you know what? I didn't measure the diameter of this compared to that. It's pretty close, though. I think I looked at that once before. Okay, that was 100 pounds. I'm going to go up to 200 now. There's 200. Okay, that's a pretty good gronk there. Wouldn't you guys agree? It's got the hum going. Let's see if you can hear that. So, yeah, that's a pretty good little wank there. All right, you know what? I just can't read it on the other side. Although I don't like the idea of standing right here, but all right, let's go to 300. Uh-oh. So that's 250. Are we losing something here? It's like it's slipping a little bit. It's 250. Let's go to 3. I'm not really going up. Almost 300. I think we're losing something here. Although I don't know what. Oh, this thing's. Let's see if I can get up to 300. Yeah, I think we lost that one there because I keep going and I'm coming up shy of 300. I'm like, you know, the resolution on this is, you know, maybe 50 pounds. Okay, so I'm at what looks like 275 here, and maybe I'll move the camera so you can see it. I'm going to move the camera so you can see it, and then we're going to, while it's under load here, I'll bring you up and you guys can get a look at this thing here. Okay, so I'm looking at this slot right here. See that? It's really rotated quite a bit. This thing basically can't turn. At least I don't think it's turning. Yeah, I don't imagine that's winding up there. It's taking up the slack, but so we're going to let it off here in a sec and see if there's any permanent deformation. We're still holding it 275. Let's take a look at that. All right, so there's a tomometer there, and let's see. Turn it a little bit there. So as I cranked up, it would go up and then it would drift back a little bit. So we're going to release this now. Is that the release one? Oh, no, that one. All right, there she goes down. And then we're going to examine this thing. You know what? This is okay. Turn the camera off, dumbbell. All right, so actually, it looks okay. It looks okay. The square is clocked off a little bit, but this thing has some general wiggle to it anyway. So I don't notice any bend in this in particular. So I think it's okay. So I'm going to put it back in, and we're gonna try to take it up a little farther. And that's interesting. So I don't know if you noticed, but it's up more. When we started, it was down like that, and we came up. Remember? You can back the video up, but now it's up more. So perhaps my anchor thing rotated a little bit, although I don't quite know how that would happen. Maybe it just distorted. Who knows? All right, let's torture this some more. All right, let's roll with this thing here. What do we got there? 200, a little over 200. Let's move that way a little. 250. Ooh. Well, that thing's like a spaghetti noodle, isn't it? Well, that was pretty cool. Oh, you know what? You know where it failed? That's kind of cool. That's interesting. Look at that. It failed at the square. Not where I expected it to fail. That's pretty interesting. So I'm going to guess that was somewhere a little higher than where we were. Okay, since I wasn't looking, it scared the crap out of me on top of it. Oh, now I got to get this out of here. Well, that was pretty cool. So I'm going to say it's a little over 300 and 300 pounds at that distance. So we'll work out the torques in a little bit. So let's see what Mr. Snap-on does. See if it can handle that. Oh, that was cool. Okay, guys. So I got the little piece out. It was actually hard to get out. I had to weld something to it and pull it out because the detent was still engaged. So it's a little bit hard to get out. I'll show close-ups of this when we're done. We got the Snap-on in now, and you know, just remember that I've set this distance so we're pulling from the same point on the handle, okay, so the same radius, okay, and this one failed at somewhere around 300 pounds, maybe a little bit more. So the first time I went to 275 on the tomometer, and then the second time I went a little bit farther, and then we had the failure. So let's take this one up, and I'm hoping this one doesn't break. I gotta get on this side here, or else I won't be able to read it. 100. There's 200 already. Okay, I'm pretty straight here. Let's see. Let me scooch it back just a little bit. So we're pulling a nice 90 degree there. Just like all the mechanics do, they pull on it exactly right? Okay. So we're at 200. Come on, baby. That's 250, 275. Pretty damn tight. Okay, things are looking okay. There's 300, yeah, almost 300. Couple clicks. Okay, there's 300 right there on the Snap-on. So just to, I'm gonna, oops, I'll bring you guys in here so you can see the meter. All right. So there's 300. Well, while I got you here, let's just go. I want to go a little bit farther because I think the other one made it a little bit. Oops, wrong way, dopey. There's 300 and something, right? What is it? I gotta look in the camera here. Oh, come on. Stupid glare. You stupid ass glare, come on. All right, so I'm gonna call that 325. All right, and I think that's as far as I wanna take that one. You know what? Screw it. Let's go a little more. All right, I'm gonna call that 350. So 350, and I'm calling it quits on the snap-on. All right, let's discombobulate this. Okay. Let's get that out of the way. All right. All right, still good. You know what? This could have went further. I don't care to wreck this. Although I think we've proven our point here. This failed catastrophically. I don't know about you guys, but if I was under a truck or up on a platform or doing something and pulling on this that hard and it let go like that, I'd be pissed. Is what I would be. I would be pretty annoyed. Now this may be an anomaly with this tool. Maybe this tool is defective. We're going to examine it a little closer here and look at this fracture and see what we can learn from that. This went to at least the same amount and shows no sign of ever having been there. So, and in fact, I've frickin' pulled on this one really hard before. I was moving I was trying to lift a press brake, a big press brake one time, and cranking on the feet to lift it up, and this thing was, wow, this one I was younger and I could actually pull on something. So let's go back over to the bench. We'll take a look at the fractures and talk a little bit more. Okay, so we're back over here. So here's our the two heads. This is the snap-on and this is the Pittsburgh. So there's our failure. Let me get my magnifier out here and we'll take a look at this here. Wow, that is just a shear, classic shear, a torsional shear. I'm looking at it, I'm trying to determine the starting point there. Man, it's hard to say. I think it started over here because we see smeared material here and then the rest looks like clean fracture, so maybe this side, and then it started to rotate and then it just failed all the way to the center. One thing I didn't check is the hardness of this. Touch it with a file here. Oh, the file definitely cuts it. Let's give this one a little, well, this has got chrome plating on it, so that's not going to be a fair test there. So I'm filing the sheared area. You know, the chrome plating's hard, so it's hard, but not so hard that a file doesn't bite. Here's the other business end here, and you see I welded a little piece of rod on there and yanked it out of there to get that out. So that was the Pittsburgh. So here's the snap-on after torture testing. I think those little marks were already in there from a previous life. Okay, this still operates fine. It goes through its motion. It still retains its stiffness. Okay, so in this case here, in this situation, Pittsburgh versus snap-on, I think you get your money's worth out of the snap-on. I really don't like seeing a catastrophic failure like that. What we would want to see is a ductile failure there, where it just yielded and just kind of did the wound up Allen wrench thing or whatever, you know, where it failed plastically as opposed to suddenly like that. So the pivot, you know, I really thought it was going to fail at the pivot here. but that seems to have hung in there. So, you know, pleasant surprise on that part there. So, come to your own conclusions, buyer beware, and if you need a half-inch drive breaker bar, this is certainly an economical choice. If you're a professional, you guys know what to do. Okay. Hey, thanks for watching. Throw up some comments. Let me know another tool you guys want to see tested in this fashion. So this was kind of fun, and that was an exciting result. So thanks for watching, guys.